attending this webcast on EMS for solenoid applications. My name is Arvind, and I will be the application engineer who will preside over this webcast. And as Dana pointed out, if you have any questions during this presentation, please feel free to type it in, and we'll be happy to tackle all of them at the end of this webcast. Okay. With this, I'm going to start showing my screen, and hopefully you see my screen. So we're going to get started. Okay. The topic for today is EMS for solenoid applications. And the agenda that we have today is we will just briefly talk about what solenoids are and what are the challenges that engineers face in this industry when they design solenoids, and how simulation can actually help them in this in their problem. Okay. So and we'll also talk about how a solenoid is actually simulating solenoids is some kind of a multiphysics problem. And we'll then delve into the EMS approach to simulation of solenoids. I'll be bringing together some advantages in this approach, and then we'll quickly look into a product demonstration where we solve a solenoid, and then we take a look into the EMWorks products, and then we'll open the floor for Q&A. No, solenoids, basically, I mean, I guess the people attending here are quite familiar with it. So in short, what is it? It's some kind of an electromagnet. It can be made a super strong magnet, and it has a very useful, it's a very useful device, and there's a plethora of applications. Okay, so it's basically a coil wound around a core, as you see in this picture, and then when you apply current through this coil, it actually creates a magnetic field. And this pretty much behaves like a magnet. Okay. That's in short what solenoid is. Okay. And when you now take a device like that, which is just a physics principle, and then subject it to some smart applications that engineers over the last century have actually come up with, I mean, you can think of many things that solenoids are actually driving today. The locks that you see, you have valves, you have MRI machines, hard disk drives, speakers, microphones. They're there in every possible industry that you can think of, from automotive to chemical industries to defense, you know, and even in electronics, washing machines, consumer products, etc. And they make it a very powerful device that can be used for many applications. So pretty much, you know, if I want to explain solenoid in less than 5 words, it's something that turns electrical energy into motion. And then we take a look at what are the challenges that engineers face today while they design solenoids. Okay, basically, you know, the concept of solenoid is quite an old one. It's nothing novel or nothing new. But you know, as the applications and challenges mount in today's world, the engineers who use solenoids for their designs, they have the following issues. Okay, one of the first challenges, you know, what kind of forces do I really get in my solenoids? You know, it's supposed to actuate things, and hence it's very important to understand what kind of forces the solenoid is able to deliver. Okay, and then once there is force and there is motion, then the next challenge is, you know, how do I predict the motion? You know, how long does the solenoid valve take to close? How long does it take to open? And things like that, which is basically predicting the motion characteristics, like the velocity as a function of time, acceleration as a function of time, etc. Then when we now come into the electrical engineering problem, is how can I study the magnetic field distribution of a solenoid? And if there are other ferromagnetic substances there, you know, how do I know what type of magnetization happens there, and so on. And last but not the least, you know, people are interested in predicting what kind of back EMFs and things like that are induced as a result of this solenoid application. So these are some of the challenges that engineers have faced over the last several years, several decades to be sure. And with the advent of computer-aided design and computer-aided engineering, the answers to these problems have become much more easy and much more robust when compared to some of the techniques that use principles of equations and so on. There's really nothing wrong with using equations to predict these things, but the challenges are those physics equations which are closed form, as people like to call them. They pretty much work on a set of very narrow assumptions. You need to have infinitely long things. You need to make sure that there is no interference. You need to understand, on a perfect world inside a textbook, a lot of these formulas work, and they're still good and applicable to a lot of applications. But in today's world, when you have devices that have to have a look that is very different from the prismatic shapes that we are used to, the accuracy of those hand calculations actually reduce, and hence the application of computer-aided simulations that's actually being extremely beneficial to today's engineers. Okay. And why is solenoid exactly a multiphysics type of a problem? Because if you just take a look at the solenoid as an application, there is a current that goes through a coil which generates a magnetic field. Okay. Now this magnetic field, it exerts some force on whatever is the actuated part or some kind of a mobile part, okay, in the solenoid. Okay. And this magnetic field which creates a force, then that force generates a motion, but when a motion is being generated, the part actually moves a little bit away, which means is basically it cuts through the magnetic flux, and in the electrical engineering term, there's a variation of the magnetic field. It's not constant anymore. So with the new position of your movable device, the program has to compute the magnetic field again, and then have to compute the forces and so on. So it's technically a multiphysics problem which involves kinematics and electromagnetics, and hence the challenge is in how do I solve these two in unison to make sure that I get good results. Now this is EMS, which is a gold partner product of SolidWorks. This is our approach to electromagnetic simulation, basically in the world of solenoids. Okay. The first step is, you create your 3D geometry using SolidWorks, which is by far the most popular CAD tool that is available in today's market. So once a 3D geometry, in this case, could be an assembly of many parts that work to make this solenoid component. Once it's designed, then you basically do a computer-aided engineering or a simulation on a computer, and this is an electromagnetic simulation on a computer that basically gives you the magnetic fields that also predicts what is the force that's going to act on the mobile part. So you can look at the results of the electromagnetic simulation using a variety of techniques, which we will actually go through in the live demonstration. You have 3D plots, you can predict back EMFs, you can get the magnetic fields and the forces, etc. Okay, but now coming to the multiphysics part of it, because of the force that was now that is now being applied on the movable part, because of the excitation of the coil, that force actually generates a motion. Okay, so there is a movement of the coil or the movement of the core or the movable part or the plunger in the case of solenoid valves, and this motion is actually simulated using SolidWorks motion. And SolidWorks has a kinematics and a dynamic motion simulation software which is available as a part of SolidWorks Premium, and it can be purchased too through other modes. And this motion basically has the ability to generate graphs which tell you how the body moves in space, which means its velocity, its displacement, its acceleration, etc., as a function of time. Okay. Now this new motion is updated inside SolidWorks geometry, so it's actually a new position, and now this new position is again fed back into EMS, and which calculates the force and then gives back to SolidWorks motion and so on. This is actually a loop that goes on till the final position of the solenoid is reached. Okay.
Arvind, I'm sorry, this is Dana. I'm sorry to interrupt you, but the slides aren't advancing, so I just wanted you to be aware of that.
Oh, they aren't?
No. that.
I have no idea. I don't know what happened.
There you go.
I don't know when did that stop? You know, do you want me to go back and? Okay, I'll keep this. Okay, I'm going to just for the benefit of some audience here who might join in, who might have joined in a little late or missed my slides. I apologize for those slides not coming in place. So we quickly wanted to look into basically the agenda. We wanted to talk about solenoids. I'll be very quick here. We want to talk about the challenges that people face in today's solenoid application, why it's a multiphysics problem, the EMS and SolidWorks approach to solenoids, the advantages, and we'll have a product demonstration. Okay. As far as solenoids are concerned, basically, in short, it's an electromagnet basically, and you know, it's made of a coil that is wound around a core, and when current is passed through this coil, it generates a magnetic field, and then it also generates forces on any magnetic material, ferromagnetic material that's there in the vicinity of the magnetic field. That's pretty much the principle of solenoids here. Because of this very powerful phenomena that this device is capable of producing, it has a lot of applications. It can be used for locks, it can be used for valves. Solenoid valves are very popular. MRI machines have solenoid valves. A lot of modern electronic devices like hard drives, etc., they operate, they have solenoids inside them. There are speakers, microphones, and if you actually take a look at the industries that they apply across, is automotive, aerospace, defense, chemical, consumer products, and pretty much it's a ubiquitous device that you see in a lot of products that deal with electricity. And then let's talk a little bit about the challenges that engineers have in designing solenoids. So basically, the idea of obtaining the forces acting on parts is always a challenge, and I had to repeat myself here, but and that's mainly because without any kind of computer-aided simulation, you have to rely on textbooks and first principles of electromagnetics, which are very sound, and there's nothing wrong with it. But the problem is there's a lot of set of assumptions that go with those formulas behind. So those assumptions today are violated in the modern designs, where we don't have components that look prismatic, that extend to infinite distances and so on. So pretty much that's quite an approximation. Those formulas that we have today are pretty much approximation, and in a real world they don't really tend to apply most of the times. The next thing is in predicting the motion. When I mean predicting the motion, I guess the movement of the solenoid valve is pretty constrained. But you know, how fast does it move? You know, how long does it take for it to engage, for it to close, and so on? This is tricky and challenging, and this is one of the challenges. And finally, to visualize the magnetic field distribution itself is quite a challenge, because unlike other things like, say, a fluid flow or a force acting on a component which bends and so on, magnetic fields are invisible to the naked eye. So it's something that one cannot visualize using the eye. So it's really hard for people to understand the concept of magnetic field. And it would be very nice if a computer program can pretty much color code and tell you what the magnetic fields are going to look like in your components, in the air region around it, and so on. And finally, solenoid people in this space also want to predict the back EMFs and things like that. So these are some of the challenges. And really, solenoid is a multiphysics problem, and that's because so there is a magnetic field, there's a force, there's a motion, and this motion affects the displacement of the part, and then hence the whole part changes. And hence this is a multiphysics problem that involves electromagnetics and dynamics. Okay. And let's take a look at now SolidWorks and EMS approach to solenoid simulations. Okay, so the 3D geometry is created using SolidWorks, and then we perform an electromagnetic simulation using EMS. which is a gold partner product of SolidWorks. EMS is capable of predicting the magnetic fields. It helps you to visualize the magnetic fields. It also helps you to understand what are some of the important quantities like forces, torques, etc. that arises due to this magnetic field. It helps you to also study the back EMFs, and 3D plots and so on. Now this force that EMS calculates based on the application is then fed into SolidWorks motion. That drives the movement of the the actuator here in this case of solenoid. And SolidWorks motion is capable of generating very rich graphs which track the velocity, acceleration, displacement, etc. of the component as a function of time. Now, when a new motion is updated and the new position is obtained using SolidWorks motion, that is actually fed back into electromagnetic simulation, where it calculates the new field and the new force, and this loop goes on till the final position of the valve is reached. So this is the EMS and SolidWorks approach to solenoid simulation. What are the advantages of such an approach? Okay, first of all, EMS is a gold partner product of SolidWorks, so it's integrated inside one interface. Okay, what that really means is you generate your 3D models, assemblies, etc. inside SolidWorks, and you don't have to take it out. You don't have to spit it out as any other file for you to do simulation. So there is no translation of geometries, there is no loss of geometry, loss of time or productivity in bringing models across various platforms. Okay. So that is the biggest advantage that one can reap in doing a simulation inside SolidWorks. And you can also perform very real-world motion simulations using SolidWorks motion. You can use springs, dampers, contacts, etc. And these are some of the things that designers typically incorporate inside their products. So you can use all of them to do a motion simulation. Okay, and finally, all the engineering results that one wants to take a look at for their designs, in this case it's forces, back EMF, inductances, etc. All of them are neatly organized and given for you right inside the SolidWorks interface. Now I'm going to just quickly go over a product demonstration. So I'll be sharing my SolidWorks screen with you, and just bear with me for a second while we go over the demonstration. Okay. I hope you can all see my screen here. Okay.
We can.
Okay, thank you very much, Rick. Okay, what we have here is an example of a solenoid valve, basically, and let me take a section view of it, which will help you clearly understand what it is. So we have a coil which is kind of a yellowish, orangish part here that you see, and there is also a movable part. In this case, this is the plunger which moves in and out, and this is the coil through which the current is passed. And what's really happening as I pass a current through this coil, it generates a magnetic field, and this magnetic field exerts a force on this plunger, which is a ferromagnetic part, actually some kind of a mild steel or iron or something. So this force hopefully is going to push this plunger inside and help it to close the circuit. So when the force is first calculated by the EMS program, it then gives the force to SolidWorks motion, and SolidWorks motion updates the new position and then hands it over to EMS, which again does a simulation to calculate the new forces and so on. So in terms of how this is achieved inside EMS, so this is where I create my geometry. This is SolidWorks. I'm sure all of you are very aware of this. This is the tab in which I can do my electromagnetic simulations. Okay. Now, one of the first steps that is required when I'm trying to do a simulation using SolidWorks Motion and EMS is to define a motion study. So I have my SolidWorks Motion turned on here, and this is my motion study area. Okay, I have to make sure that the motion analysis is there, and I just apply a force acting on the movable part, in this case plunger, and then I give it a value of 0 newtons. And now you might be thinking, you know, what is the point in applying a force of 0 newtons to a plunger? Okay, the idea is this is the way by which I tell the EMS program that you know, or SolidWorks Motion program, that the force of 0 newtons that is being applied is now going to be substituted by a value that EMS is going to give it. Okay, and then this is the force that SolidWorks Motion is going to apply to drive this part. Okay, so it's basically a 0 newton is just a placeholder value that tells SolidWorks Motion that you know, you're going to get this force from some external program, in this case EMS. Okay, and as far as EMS simulations are concerned, they're all organized as studies. Okay, so this is a study which is basically there's a name for it, and then if you are interested in computing circuit parameters like inductance, etc., flux linkages, back EMF, and so on, you would check this. And this is the most important thing: you can couple any EMS study to SolidWorks Motion. So here I ask it to couple it to SolidWorks Motion, and then I've created a study which creates a study 3. Once the study is defined, then the next step here is to apply materials to my components. Okay. Okay. So first, let us take a look at some of the components here. So all of these parts are applied. This is mild steel. So everything that is movable and stationary here, other than the coil, is mild steel. So let me go back and turn my section view. That helps us understand what it is. So let's take a look at the material library inside EMS. Okay, so when you go ahead and apply a material inside EMS, so this is a customizable material database that is included with the product EMS. Okay, so here you have some conductor materials, we have some ferromagnetic steels, you have some ferromagnetic materials, you have permanent magnets, you have a lot of customizable and out-of-the-box materials that is provided for you in the simulation. So we make sure that we select mild steel for the parts that that are definitely for the movable plunger and also the stationary parts here. And then when you come to the coil, we apply a conductor material to the coil. In this case, copper is applied to the coil. Okay, and then you also have you know that the magnetic field resides not only in these ferromagnetic materials, but it also is there in the air region around the model and inside the solenoid. So it's kind of important that the air region is also modeled using SolidWorks, which is actually being done here. So I have an air region that just envelops inside the solenoid, in and around the solenoid, and I have a big air region. So the objective of these two air regions is to also capture the magnetic field that exists in this air and the air domain as well. Go ahead and hide this. Once you have defined the materials, the next step is in defining the force. Basically, we are going to tell the EMS program to compute the force on this particular plunger. In this case, it's highlighted in blue in color. Okay, the objective is to compute the force acting on this plunger. Okay. Now coming to the coil definition. Okay, so this is a coil. Basically, we have a coil that is modeled as just an annular cylindrical ring, and the program allows you to specify many things inside a coil. So it's a current driven coil, so you can have both a voltage driven coil as well as a current driven coil. Obviously, the coil is made up of many wires that are turned. So if you have the wire gauge of those wires, this is where you would enter them. Okay. And we select the components that comprise the coil. In this case, the annular blue color part. Then we talk about where the current enters the coil. So this is the entry phase. And basically, it's a complete coil. So the entry phase and the exit phase, it's the same port as the current. So it's, although we are looking at it from a cross-sectional point of view, we have a complete coil, a wound coil. So the current is just circulating in that wound coil. Then finally, we specify the number of turns, in this case 100, and what's the current that's flowing through per turn. Okay. So this is the definition of a coil. Once the coil is defined, we are now ready to solve the simulation and then get the results. So I have done the solving beforehand in the interest of time, and now we can just go straight into the results. So one of the first things that one can take a look at is the result table. Okay. A result table is a place where we organize all the results, both the electromagnetic results as well as the motion results are organized in the result table. For example, if you want to understand how the, for example, the force acting on the solenoid, how does it vary? The force in the z direction, in the y direction is the important component here. So this varies as a function of time. So basically, as the solenoid moves in, the force varies as a function of time. And you can actually plot the force as a function of time and take a look at how the variation of force is as a function of time. So it's the value is minus because it's in the motion is in the minus y direction. So the main XYZ is here, and the solenoid has to close, so it's in the minus y direction. This is how the variation of force is as a function of time. Okay. The next important thing that one can calculate is the back EMF. So the back EMF of the coil is computed at every time step. So you can also decide to plot the back EMF as a function of time. So as the coil goes closer and closer, the back EMF keep increasing, and that's what you see here till it comes to a complete position. Okay. One can also compute the inductance of the coil. So at every time step, and these are the circuit parameters that I talked to a little earlier. So inductance can be studied. The flux linkages associated with the coil is also computed at every time step. Okay. In addition to these parameters, some of the motion parameters is also there. For example, if you want to understand the velocity of the solenoid as a function of time, we can plot them. So the velocity as a function of time is actually plotted here. Obviously, the velocity again is in the minus y direction. Okay, and this is plotted as a function of time. Okay, and this is where we organize all the results. And the next step is, this is a three-dimensional field simulation software. You know, SolidWorks is a 3D CAD, and the fun of doing 3D simulation is the ability to visualize your results in a 3D space, and that is possible. So one can actually take a look at the magnetic flux, for example. How does it vary inside my solenoid? So in this case, I have a section view. I've created 2 section views to study the magnetic flux and how it varies inside the components of my solenoid. So I can actually choose to animate this magnetic flux, and this will be very clear now as that predicts the motion of the solenoid. So here you see that the plunger is, as soon as the excitation is turned on, there's a force acting on the plunger, and the plunger keeps moving inside, and as it moves, there is an acceleration. There's more and more force as more of this cuts the magnetic field generated by the coil, and this accelerates the plunger and allows it to close. And you can see how as the plunger moves close by, there is some magnetization of the steel, both the movable part as well as the stationary parts here. And all of those can be actually studied. And one can also take a look at from a point of view of vectors. So here is the same plot of the magnetic flux density, but now more as a vector. So vectors probably help us to analyze or visualize the magnetic flux and magnetic field, etc. in a better way. So one can actually do that. And you can animate these things too. So notice how the vectors grow in size as the solenoid comes close by. Okay. So in addition to the magnetic flux density, the program allows you to plot the magnetic field intensity. Here we can plot the magnetic field intensity again as a section plot, but now you notice that I have this thing on the entire model here. So this is the magnetic field intensity, as the units here is amperes per meter, and this is the section plot. Again, any of these plots can actually be animated to visualize what's really happening as the motion of the solenoid is going on. So notice here that the scale changes, and you can literally visualize what's happening here. So and you can take a look at the force densities plot, the current, the applied current, and so on. So there's a lot of plots that are available for you to visualize. Now the magnetic flux and things that we saw in the part, and you can also take a look at these things if you have the air turned around. So I'm going to go ahead and show my air. So these things are also there in the air region, and you can take a look at for example, the field intensity. Not just inside my solenoid in all the components that are there, but also in the air region. So you can see that here, the field intensity. And I can turn on my the larger air part. And you can really see the sphere of influence. Basically the blue regions tell you a very low value, and this is how the magnetic field intensity is. So, okay. And you can also plot the vectors. So it's not just the vectors inside the solenoid, but also in the air region around it. But again, the sphere of influence is very little outside the solenoid. And so you can take a look at that. Go ahead and hide the components of the air here. Last but not least, I want to show you a very useful feature inside EMS, which is the automatic report creation. So I can actually generate a report automatically, either in HTML or Microsoft Word format. And when I ask the program to generate a report, it automatically captures all the plots and all the simulation results, and then spits out a nice Microsoft Word file that can be edited here right inside SolidWorks. And you can add your comments. What it contains is the information of the model, all the how does it look, the parts, that the components and its materials, the coil information, the force values that are the force values, Fy as a function of time is here. So pretty much the back EMF, all the results that I showed you earlier is captured in a nice Word format, and even the plots are captured, and this Word file is saved along with your model, and it can be accessed from inside SolidWorks. So this is precisely one demonstration of our product, and which I wanted to show you, which is more relevant and meaningful to solenoid. And if you were to do a design change inside SolidWorks, you can do that and your simulation and do your simulation for your new design, and you can compare and do many things inside EMS. Okay. So with this, I'm going to go back and revert back to my slides. We end this we end this product demonstration, but I have a few more slides that go to tell you about the product bundles and so on. But if you have any questions so far, please feel free to type them in, and I'll be able to handle them at the end of the session. Now let's take a look at some of the EMS products and its bundles. Now the EMS product portfolio itself contains two different products. One is the EMS Professional and other is the EMS Premium that you see here. The EMS Professional comes with 5 different solvers. It can do electrostatic, electric conduction, magnetostatic, AC, and transient magnetic. So basically, no matter what your excitation is, whether it's DC, AC, or any current as a function of time like pulse input and so on and so forth, can all be handled by EMS Professional. In addition to it, the EMS Professional can be coupled to motion. For example, what we saw now, it can be coupled to steady state thermal simulation. So if you want to understand how hot your coil gets, how hot your component gets around the coil, so that is possible. It can be coupled to motion simulation, what you saw here with SolidWorks Motion. That's an add-on. And very soon we will be having a module that couples to structural simulation. So the electromagnetic forces can actually be fed into a structural like FEA-based program that can actually compute the stresses, the displacements, etc. on your geometry. Okay. All the EMS products come with activation-based license, but there is also an opportunity, should you need, we provide network license also. The EMS Professional, the Premium is nothing but the EMS Professional with both the thermal add-on and motion add-on, and when the structural add-on is there, it's going to be inside the Premium too. Obviously, when you buy them as a package, like a Premium, there is significant cost benefits to buying Professional and adding some of these things. And we also have a product called HFWorks, which is in the RF and microwave space, I guess, which is not the topic for today, but maybe at some other point we will be doing that type of seminar too with TriMech. And these are the products and bundles that we currently offer. Okay. So basically, another question would be, to be able to do what you showed me today, what would I need? Okay, so what you would need is the following. You would need SolidWorks 3D CAD with preferably SolidWorks Premium, because that would have SolidWorks Motion Simulation inside it. Or I guess you could probably purchase SolidWorks Motion Simulation separately if you just had the basic SolidWorks. And what you would need is the EMS Professional and the EMS Motion Simulation add-on. Okay, this is what you would need to see to be able to do what I showed you today. And then last, I would just like to thank you all for taking your time today to attend this presentation. You feel free to visit our website, emworks.com. We have white papers and customer testimonials in there. And also you can access our YouTube channel. I think we have over 30 or 40 videos there demonstrating various concepts of the program and the various functionalities. So please feel free when you have time to check these things out. And should you think that our solutions fit your need, always please contact your local SolidWorks reseller. In this case, it's going to be TriMech Solutions, and we'll work with them to make sure that your needs are fulfilled. Okay. With that, I'm going to take some questions that have come up during our presentation. If there are any questions, please feel free to type them in and I'll be answering them.
All right, are there any questions out there? We'll wait here a couple minutes. Also, I wanted to tell you all that this is being recorded and you can find it on our YouTube channel. You can go to our website, trimech.com. Upper right-hand corner, you will see our Facebook, Twitter, and LinkedIn accounts, and also our YouTube account. You can just click on it. You can view this and all of our other webinars that we have done. Arvind, you did such a great job with this presentation. I don't think there are any questions out there for you. I just want to thank you all for joining us this afternoon, and I hope you have a great rest of your day. Bye-bye.